So before we start, I believe I need to give some introductions, and I would really love to hear about you folks. My name is Dmitry. I'm working at Intel Corporation for the last, I don't know how much time, maybe for 5 years or something like that. We were acquired formerly an ITSIS corporation or ITSIS company in Nizhny. And that company supported OpenCV since 2005 till 2016. And then OpenCV maintenance has moved with Vadim Pisarevsky, I believe you know him, right? To Intel, back to Intel, where it was originally started. I will share some bits of history during my presentation. And in that team, I'm leading this G-API design, development, and productization, like the overall model from its early beginning for Intel platforms. So we introduced it in OpenCV in 4.0, which was released in 2018. And since then, we are developing G-API as a graph engine for OpenCV, where we explore some new, different ways of doing and executing computer vision, which is friendly to the hardware platform. So I will share some bits of that as well. Okay. So in this talk, we will cover the basics of G-API. I will try to explain why it exists at all, so why we decided to introduce this model in OpenCV. Then we'll cover some very basics of programming with G-API, so very basic concepts which are enough to build quite complex pipelines with G-API. Then I will walk through particular features which are especially interesting right now. It is inference and combining DL models with classic computer vision, and a streaming execution mode, which we believe have lots of profit to use. Then there will be a short mention of the Python API, which was recently introduced. So this presentation was updated to version 4.5, which is one of the latest ones. And I will also mention our current features which are in development. So you will get the idea of what and where we're moving forward with the G-API development. And then some theoretical, practical data on where G-API really shows benefits. So finally, if we have some time, I will give some demos if the time permits. So I have prepared some examples which I can walk through and demonstrate how it works on my laptop, from which I'm sharing this session. Okay, so let's start with some bits of history. I will try to explain the very brief history of OpenCV. So since you're OpenCV team, you might be aware of that already, right? From Vadim's maybe talks or memoirs. I actually cleared up this slide with Vadim when we initially wrote that. So it is kind of Vadim's approved. So OpenCV is at version 4.5 now. So it has a long history. It turned 20 years last year. So we had the celebration around OpenCV that it turns 20 years. So, but it wasn't that OpenCV 20 years ago, right? 20 years ago, it was plain C library, right? It was not as big as now, and it was not a C++ library. It was just a set of individual functions which you can call and run individually, and that was C functions. And those C functions run immediately. So when you run a C function, it does something and then produces the result immediately. So this is what was OpenCV in version 2.x 20 years ago. And it was quite useful already because there were no any available collections of computer vision functions right now at the market. And there are plenty of useful utilities around that, right? Reading files, writing files, displaying images. So it had a pretty decent basis to explore and experiment with computer vision at that time. However, the evolution is kind of unstoppable. Okay. Let me know if you can hear me or cannot hear me, because I see this messages popping around that my connection may be not stable. So I'm wondering whether I'm still presented or not. So in version 2.x, which was released a couple of years later, OpenCV has been rewritten to C++, and its cornerstone structure has become CVMAT. I believe everybody is familiar with it right now. But at that time, it was something new. So OpenCV has become more object-oriented. So the old IPL image, IPL stands for Intel Image Processing Library, something like that. So the OpenCV origins from Intel optimized libraries, which were developed by Intel somewhere in 90s. So everything has been wrapped into C++ interface. CVMAT allowed to manage memory buffers properly and allowed to wrap the data processing inside so that it becomes more complex and more useful API. However, the execution model of OpenCV didn't change at that time. It was still a library of immediate mode functions, and when you run a single function, it is just doing its thing, right? So if you run filter, this filter runs and completes. If you run some resize or some transformation, some color space conversion, it just executes, and you have this new CVMAT in your hands, like the immediate result of that function. So in version 3.0, which was released somewhere in almost 10 years ago, time flies, a transparent API has been introduced where CVMAT structure has been extended with UMAT. So every OpenCV function in core started accepting not only CVMAT like it used to be before, but also UMAT, which is like a transparent replacement to CVMAT. And by using UMAT, you could easily move your code to OpenCL because OpenCV has become OpenCL aware. The internal functions has get those OpenCL versions. So if you pass a UMAT buffer into an OpenCV function now, then if it is possible, it runs on GPU or on some OpenCL compatible device. So it allowed this transparent transition from individual code, from individual functions to some queue-based model, where when you run a function, it kind of executes immediately, it terminates, but the task is asynchronous. It is pushed somewhere to a queue instead. Right? And when this UMAT is produced from that function, the data associated with UMAT is somewhere in GPU. So when you pass this result of this function to some other function, then it can consume this result directly from GPU without any extra transfers. So this was the idea behind this transparent API. So OpenCV has introduced this model to share data between different functions and run them asynchronously with a tiny code change. And finally, in version 4.0, we introduced G-API. So G-API was not a library, right, like it was in the previous two versions. So as I mentioned, it was a C library, then it has turned into a C++ library. Then finally, that C++ library has been entirely updated with OpenCL capability so that you can pass a UMAT instead of CVMAT almost in any function, and it kind of works. So G-API is different because it wasn't like some full library, right? Instead, we introduced a new model atop of what was already available. And this model is something you can use or you can not use. For example, if you don't want to use Graph API, you can continue using the old OpenCV, or the traditional OpenCV, with no any extra overhead. However, if you want to leverage this extra capabilities of the graph model, then you can start using G-API. And the idea of G-API was to make this transition smooth. So if you have your existing OpenCV code already, then it should be quite easy to move from the old OpenCV code to this graph-based model if you want to. So the history continues with after the version 4.0, and in version 4.2, we introduced this inference capability for OpenVINO toolkit. So we are working at Intel. We have this OpenVINO inference engine as one of our flagship software products for inference. So it was natural and quite natural to extend G-API with support for inference and to support OpenVINO toolkit as a vehicle to run this inference. So previously, G-API was only limited to computer vision functions like classic image processing, image arithmetic, and that's it. There were quite a few cases where it really ran well on that scenarios. However, the world changed, right? And lots of algorithms have become DL-based. Lots of classic algorithms has turned into deep learning algorithms where you just need to run a single model and kind of connect this model with someone else. So in version 4.2, we updated G-API to have inference as part of the graph which G-API executes, and extended it with video-oriented capabilities. So previously, you just pass a single image to G-API and get the result from the entire graph. Now you can run a G-API graph on the entire camera stream or a video stream or whatever stream for whatever data source you can connect to the G-API. So it becomes some really pipeline model. And this trend continued in the further version. So we added some more video-oriented capabilities, which are either can be or cannot be exposed right now. So the public version of OpenCV, which is shipped in OpenCV, is just like tip of the iceberg, right? So for Intel-specific platforms, which are in development, there may be more functions available, but we just don't release it. It is not in the public version of OpenCV right now. And in version 4.5, we introduced Python interface. It was a full-featured Python interface, which allowed to build, run, execute those graphs in Python, as well as extend them with Python code. So now, if previously it was a C++ only interface, which was not very friendly for novice users, and Python gained some more and more adoption in this area, we decided that Python is a way to go, and now Python can be used as a primary language to program with G-API, including writing custom code, which you can plug into the graph, which executes. And finally, some more media-oriented data structures and capabilities have been introduced in this release to pair G-API with more media formats like NV12, IUV, etc., without changes in the graph model. So it unblocked us with codec support, cameras, and different accelerators, which we currently develop here. So the question is why we had to introduce this graph-based model at all. So the answer is that the graph model allows us to look at the whole algorithm, and we as application developers or as library developers can look more into what user is doing and offer some more ways to optimize the code flow. Because previously, as I explained in this historical section, OpenCV was a set of individual functions. As a library developer, you can only optimize this individual function and nothing else. And the way how those functions are called together, this is what you don't know until version 3.0, where this transparent API has been introduced. However, transparent API is actually dynamic. So when you run those functions on UMATs, the framework only enqueues OpenCL kernels into a shared queue. But the framework or the library have no any context about how much kernels are yet to execute, what is the structure of this workload, how those operations are connected together, and what extra optimizations can be applied to that. So in order to provide library with such information, we brought this graph model to OpenCV so that this G-API engine now can analyze and apply those optimizations to algorithms if those algorithms are implemented with G-API. So just a summary of what I said already. There are a number of ways to optimize a library from a library developer's perspective, I mean from the ours perspective. We can put optimizations to individual functions, we can vectorize them, we can put some trading into them. However, the scope of that optimization will only be limited by that single function, like by a single resize or by a single blur, by a single, I don't know, morphology operation. So we cannot bring optimizations at the pipeline level when developer starts using that functions. it just solved it a little bit with a queue-based approach, where when developers are starting using this asynchronous transparent API, starting with OpenCV 3.0, when kernels are enqueued into a queue and then are offloaded to, for example, a GPU device. However, the graph model is what we can get this structure of the algorithm in its entirety, from start to end, from top to bottom, and see what are the functions which are used there, how much memory we need to allocate, how we can optimize this memory access for the whole graph. So this clear picture only visible at that graph level when we transform algorithm from those individual functions to a graph. So all this points where we can optimize our list on this slide. So as I mentioned, there are several optimizations for the memory consumption. I will explain it later, and maybe we'll demonstrate it with a demo. The parallelism can be applied to the whole graph, not to individual functions. And when it is applied to the whole graph, we gain some better core locality, better cache locality, and it also gives some points on traditional CPU architectures when you locate the workload in a single core. And if you have multiple cores, you can split it to gain some better locality and to avoid this cache misses between different cores when the algorithm is properly distributed across the cores, with no any extra interconnect between those cores on the runtime. And heterogeneity is also a very important point. Almost all platforms today are heterogeneous, so it means that on a single SoC, on a single processor you buy or you get in your laptop, you don't only have the CPU, right? There is also a GPU, which is maybe integral or maybe discrete one, which can work in conjunction with CPU. There may be some specialized accelerators like VPU, which Intel provides, starting with Myriad 2, then Myriad X, and any other further generations. So there is ISP on CPU, which can be used for image processing when we're triggering camera. So modern processors are heterogeneous, and heterogeneity means that there are different blocks on this SoC which can run in parallel. And in order to maximize the performance we want to get from that system, we need to load those blocks to the maximum. We need to properly distribute the work between them. And we need a way to specify that I want to run this functionality of my algorithm here, and I want to run this functionality of my algorithm here. And then it becomes a problem because you have two different environments, two different execution environments, two different memory types you have to conduct. And for programmers with a little experience in system development, it may become tricky. However, with frameworks like OpenCV, we're trying to make it more acceptable, more easy for developers who are not very good into this platform details, but want to leverage this platform capabilities from the silicon they have in their systems. So I hope it is all for introduction. Not sure if there are any questions already. Oh, so yeah, we can start with actually diving into this concept of G-API. So first of all, as G-API, well, G-API stands for Graph API, and it is all about graphs. However, there is no graphs really in its interface. So it is C++ model in OpenCV, which allows to run CV algorithms in a graph-based manner. However, we don't force users to operate with graphs. Instead, we use some embedded or internal domain-specific language to express those graphs. So it is actually based on expressions. And those expressions are very close to functional programming languages, or maybe even Python. So there are two main concepts here. We have data objects in the graph, and we have operations in the graph. So data objects are consumed by operations. So we pass data objects to operations. And when operation gets its data objects, it produces its outputs, which are also data objects, like plus you have two inputs for operation plus, and you have one output for operation plus, which is a sum of its two arguments. And we follow the same approach, and our operations in G-API are usually look like functions when you pass data in, and you get some data from that functions. However, the difference is that the graph is not executed immediately. And when we trigger those operations, we don't run them. We build a graph. We accumulate the information about what we will actually run. So in order to demonstrate it better, let me dive to the first example. Right? And this is a very basic example of how a single graph in G-API can be executed. So it starts like a standard OpenCV application, but we have to include some extra specific headers. There's standard main, and as far as I see, this application takes two command line arguments. One is for input file, and another is for output file. And how the graph looks like. We start graph with some empty data object. In our case, it is gmat. So gmat in stands for like empty data object, which starts the graph. Then we get our output, which is also a gmat. So we write gmat out equal to CV G-API blur. Then we pass this input object and parameters to this blur operation. So that's it. This is the way how we build our graph of a single operation. So we started with some empty object. We applied blur on this empty object, and we've got output. So in this way, we've got a graph of 3 nodes actually: input, arrow, blur, arrow, output. So it's a linear graph. And what is important here is that at this point, we don't have any data. We don't have any buffers. We don't have any images. We only created some functional dependency between in and out. So then G-API knows that out, this object is produced by blur operation, which consumes in. And if this in would be a result of some other operation, then we would unroll it back to these origins and see where this in comes from. And maybe we should do something else before we calculate blur. So this is how G-API internally gets the structure of the algorithm. We unroll it back based on these functional dependencies, and we build the structure, the graph structure internally. So user is not forced to operate with nodes, edges, connections. Instead, users have to write code, functional code like this. So then we actually read data in the real buffer. So gmat never holds data. Gmat is a graph data type which represents an image or a tensor, if we're talking about deep learning. So gmat is only used to describe a graph. For real data, we still have our standard OpenCV CVMat, which we read from a file, which is the first argument. And our output mat is empty. We can leave it empty because if it is empty, then as in OpenCV, G-API can allocate it to the proper size. What we do next is that we declare our G-computation object with input and output. So inputs and outputs are specified in 2 vectors via special modifiers, G-in and G-out. If we have multiple inputs, we just enumerate all of them here, like input 1, input 2, input 3, and whatever. And the same applies to multiple outputs. So we can have multiple outputs in our graph and enumerate them here as well. So we construct a G-computation object, which actually becomes our graph. And we apply it immediately on this data. So this G-in and G-out are lowercase vectors. So these vectors denote data vectors we need to operate with. So this G-in and G-out standard with capital G are used to declare graph. And this G-in and G-out with a smaller G are used to describe input and output data vectors which we want to process. So we have a single data object as we defined in our graph. So we pass a single input matrix. And we have a single output object as we defined in our graph, and we pass a single output object to store result in. So in this case, this apply returns immediately. the graph is over, and we are ready with our result, which we write to disk. So that's the idea. Comparing some harder example with OpenCV, we can find that OpenCV G-API is very similar to the traditional OpenCV interface. So we trying to follow the same naming conventions, the same parameters, and the same behavior for the functions which we expose. And by default, OpenCV has core and improc models, which host most of the image processing functionality, this classic functionality. So we expose its analogs, the graph-based analogs, in the same header files, core and improc. However, under our own model, under G-API. So the algorithm, on this slide is Sobel edge detector, which is very basic, very classic algorithm in traditional computer vision, where we just run two derivatives. We calculate two derivatives on the input image. Then we multiply these derivatives by itself. Yeah, so we multiply jx by jx, and we multiply jy by jy. We add them, and then we calculate the square root, which is our magnitude. Then this magnitude is converted to U8, and we write it down. I will show the example of this code running later in the slide. So we'll get some edgy image of the picture we passed as an input. Speaking of G-API alternative, this is how it looks like. So we start with empty input as usual. We run Sobel twice for different directions. So to calculate different derivatives, so it is jx and jy. Then we obtain magnitude by running this SQRT operation of jx squared and ji squared, sum of them. And then we convert it back to U8 data type because it was 32F after the Sobel operation to display it properly on the screen. So the code with G-API is maybe even more compact to OpenCV. At least you don't need to declare the output object every time before running the function. You can run it in place, and you can run functions or operations in expressional manner like here. So we can combine functions with operators, again with functions. So it is really easy to write code like this. It's just very close to its original mathematical notation. So G-API tries to mimic OpenCV, and we continue following this convention. So all these new versions of G-API continue following this OpenCV naming convention. And graph can be constructed without any data. So as I mentioned on this slide, we first create a graph and then we execute it. So there is no data at this point where we defined our input. There is no data and there is no any actions taken here at this point where we defined our output, which is the result of our graph. So we first defined the graph, we defined an object which stands for this graph, and then only then we can read image, for example, from the file and apply our graph to that file, to that image. So we can build our graphs without any data in mind. In OpenCV, we also need this data to be present in our functions in order to build some algorithms. So it is always an immediate mode. In G-API, we can keep the code separate from its actual execution environment. And it was one of the reasons why we introduced that graph model, because the code we can write once. However, the execution environment may be completely different based on settings, preferences, and the case. And we don't need to change algorithm to handle that. We don't need to rewrite this code if we have some different use case or different platform where we need to run our code. Instead, we can just customize the way how the whole graph is executed using some extra parameters, or the framework will do that for you. And this logic can stay intact. It can stay the same. So that's the idea. Okay, let's go next. So for graph data types, we have dozen of them supported. GMAT was used in an example. It stands for image and for deep learning tensor. There's also, well, in OpenCV, it is represented by a regular CVMAT. So if a graph starts with GMAT, then we need to pass a CVMAT in. If the graph starts with G-scalar, it is a CV scalar object we need to pass in, and same for output. If our operations produce a G-scalar, then if this operation has been made output of the graph, then in runtime we will get a scalar object out of it. So there is also a template type supported for arrays and user-defined data. Arrays are dynamic data structures. We don't know their size in advance, so we only can allocate some, I don't know, placeholder for them, but don't do any optimizations on them. So for CVMAT, the size of CVMAT is determined at the time when the graph is compiled. The graph is compiled when we run it on the real data here. So the idea is that when we compile our graph internally, we know for which kind of data it is compiled for. For example, what is the image resolution we're processing, what is the image data type we're processing, how many channels we have, and so on. And based on that, we can allocate some proper buffers, which we will reuse from execution to execution, or even optimize the size out. For dynamic structures like vector, it is not possible, so there is not so much optimizations available for types like this, but those types are pretty useful in connection with inference. For example, when we run object detection on a frame, and then this object detection is a GMAT, then we parse this object detection results into an array of rectangles, and then we can iterate through this array of rectangles using the standard C++ means. So this is where this GArray structure is mainly used. GOPAC stands for user-defined data. Again, since it is a template type, G-API has no any insight of what is inside. And it is usually used with some custom code or custom operations, because I don't know any complex algorithms where a custom code would not be required. And G-API allows to mix custom code with G-API code, where both exist and both run in the same environment. So G-API can still apply optimizations to G-API operations, and the custom code can follow these rules and run as part of this graph, however, with no any extra optimizations except graph by trading applied to this operation. And finally, one of the most recent structures is G-frame, which describes some media data we can get from camera or from codec. And in runtime, we have a CV media frame structure, which stands as its host site or buffer type. So when a graph is defined using a G-frame, like it starts with G-frame, a media frame object should be passed in for execution. So as I mentioned, graphs are built with operations and data. And operations are, in fact, interfaces. So we have seen these operations already in our previous examples, like subel, sqrt, multiply, and convert to. But the key thing here is that these operations only denote what to do, but they never say how we will do that. So when we have a graph like this, we know that there is a subel operation, there is an sqrt operation, there is multiplication, there is sum, and there is a conversion operation. So operations only say what to do, and how this operation is executed and how it is actually implemented, what instruction set it is using, it is different. And we have this hierarchy of operations and kernels. So speaking of theory of object-oriented programming, operations work like interfaces. So with interfaces, we can express something abstract. And until we are using interfaces, it is abstract. However, interfaces cannot work, and we have to replace interfaces with some implementations, with some entities which implement those interfaces. In terms of G-API, those implementations to operations are kernels. So graph is built of operations. So graph is always built of operations. And when the graph is compiled, we look for kernels which may implement this operation. So operation A, say it filter or resize or square root, can be either implemented with, for example, OpenCL backend, and it will be one implementation of that operation, or it can be implemented by OpenCV backend, which is the default one. And then it will be another implementation to that operation. And when the graph is compiled, G-API looks at what is available currently on this platform or on this particular setup. And if there is some custom implementation available for that operation, in other terms, if there is some kernel available for the operation, then G-API is using it. This is a way how we can map easily this graph to a different instruction set, for example, or to a different platform, or to a different SOC by using a different kernels which will implement Sobel, square root, multiplication, and so on. So it works like a hardware abstraction layer, but in a very object-oriented manner. It is easier to demonstrate how we can implement one operation with two different kernels. So we'll start with the way how operations are defined. So operation itself does nothing. We only register that we have operation of certain type, which have this kind of input and this kind of output. So this syntax is very similar to std function as it is used in C++. So in this case, we defined a square root, which takes a single image and produces a single image. If we have multiple inputs, then we can put it here with comma. It will be just a list of parameters. If we have multiple outputs for our operation, then the return type here is a tuple. So operations should return tuples if there are multiple output types. So for example, Sobel xy, which calculates two derivatives at once, have two outputs, and it is defined with a tuple. Operation has only few bits of information inside. So it is a type. So every operation is a type in terms of C++. It is a signature, as I defined, which defines what kind of inputs and outputs this operation has and produces. And internal string ID, which is used to uniquely identify this operation within G-API. Finally, there is a single method needs to be provided within an operation, which defines how the metadata changes when this operation is applied. So since G-API is kind of graph-based compiler, we trying to use as much as information during this compile time in order to properly apply optimizations. And one of this is this image metadata. So every image has its own metadata, like a single buffer may have size, type, number of channels. So we want to know this information in advance. And when the graph is compiled, this metadata is collected from these inputs of the graph, which we have available at that moment, or we can specify them directly. So the graph is compiled to the certain metadata. So the graph is prepared to process images of a certain size and only, or the graph is prepared to only process data of a certain type. So this information is defined by these descriptors, and when some data is processed by operation may alter this information. For example, resize changes the size of the image, right? Or convert to operation change the output type of this of the image. So in this case, in order to properly propagate this information in the graph, we have to supply this extra callbacks in our operations to describe how our data changes when it comes through this operation. So for square root, we don't change anything. We don't change dimensions. We don't change the type. It is 32F. We don't change the number of channels. So the image metadata is kind of unchanged. We do get a new image, which is a square root, a pixel by square root of its input. However, it is still described by the same terms. So in this case, we return the same input descriptor as we get it. So this operation doesn't change anything. In other operations, you can find that this input descriptor is changed by some new size or some new type, or it may be of some fixed type. So it's just advanced topic. So after we registered our operation, we can start using it in our graph using this on method. So this is the type, gsqrt is a type. We can run gsqrt .own in order to use this operation in the graph. So in order to allow Doxygen comments, we usually in G-API provide this single line mnemonics over the operation. So in fact, this G-API SQRT, which we've seen earlier in this code, is just a wrapper over this gsqrt on method call we get automatically after we defined our operation. And it is also useful to sometimes run functions in G-API, like here. This is taken from our phase beautification example, where the single function, when it is called from the G-API, may expand into a subgraph. So here in this function, we take a gmat and a number of scalar parameters. Internally, we run median blur, we run Laplacian on this data, and we run this complex arithmetic involving the pixel-wise subtraction and pixel-wise multiplication for the subject. So when this unsharp mask will be then used when the graph is built, it will be automatically replaced with some subgraph, which is defined here. So it is one of these tricky points of this expression-based API. So after operation is defined, we can actually implement this. And in order to implement this, we have different backends which can run those kernels. So the default kernel is OpenCV backend. So the default backend is OpenCV backend, which is using and running the OpenCV functions. So every backend has its own API to define kernels. And in OpenCV backend, we have this G-API OCV kernel macro. This macro takes two arguments here, which are the type of this kernel, which we have to define, because as operations, kernels are all tool types in C++. And the reference to this interface which we are implementing. So this is the gsqrt kernel, which we defined earlier. Sorry, the operation we defined earlier in the slide. So every backend defines its own way how the kernel is executed. In OpenCV backend, our kernel signature, as it is defined in the operation here, translates into this sequence of CVMaths. Sorry. So we have a CVMath for input and we have CVMath for output. In the same way as we defined here, we have this input CVMath and we have this output CVMath. And here we can just call a OpenCV function, which will run this SQRT operation immediately. So why would we need this useless backend? Why we won't use OpenCV here at all? So the idea is that with OpenCV backend, we can prototype our algorithm easy. And if we have OpenCV or OpenCV-like functions available in our existing algorithm, then we can drop it to this operations and compose a graph of them quite easily. And after that, switch a backend or use another one, or further explore the capabilities of G-API, but the transition will be already made from this individual OpenCV code to a graph model. Another backend which is available in OpenCV and works out of the box is so-called Fluid backend. The Fluid backend is a very custom backend for CPU execution, which changes the way how kernels are executed. So if in OpenCV backend, we could run our kernels on the whole images, So we get this whole input buffer and we get this whole output buffer, and we have nothing to do but to run this OpenCV function. It's just quite naive. In Fluid backend, we have some more intelligent way of execution where the Fluid backend triggers kernels row by row. So the OpenCV backend assumes that kernel is a full image kernel. So we operate on the full image here. However, the Fluid kernel assumes that it works on a couple of lines, as defined in this window constant. So the idea behind Fluid backend is that we don't need the entire image to be present in memory in order to process it. For most of the arithmetic kernels and for most of the image processing kernels, we need a small window, a couple of lines of the image, and a small output buffer, for example, a single line of the image, in order to process it. And then Fluid backend organizes execution in that way. So these tiny kernels are executed in pipeline so that they produce the entire image. And in this case, we don't need to allocate the entire intermediate buffers, which may take hundreds of megabytes or even gigabytes. We can only allocate a few kilobytes of memory and keep execution local to that kilobytes and properly manage buffers with these tiny kernels which operate on a single image line or on a couple of image lines. So this is the idea of Fluid backend, and the same SQRT kernel would look like here. So instead of the whole CVMAT for input and instead of the whole CVMAT for output, we get a special object view, which is object specific to this particular backend, and the buffer, which stands for output. So we get some pointer to our input line, we get a pointer to our output line, and we pass it to maybe a standard OpenCV function which runs on a single buffer. Or we can run this internal cycle, the inner loop, by ourselves. So it doesn't make any difference here. Or we can run this single cycle over a single image row with some vectorized code as we do in our optimized Fluid kernels. But the idea is that those kernels consume and produce a tiny portion of the image, like a couple of lines or maybe a single line. And the execution around them runs those kernels in so way that we don't need to allocate the whole image, especially if we have a large graph with lots of intermediate buffers which we don't really can provide or consume. So on smaller pipelines, it is not that visible. On some large pipelines where we have 20 to 30 operations, it really makes a lot of sense. So still here, this run signature is defined by this SQRT definition. So we have a single GMAT object as input and a single GMAT object for output. In this case, we have a single view for input and a single buffer for output. If we would have a binary operation like subtraction, we would have two views here and a single buffer for output, because this subtract would be defined as GMAT parenthesis GMAT comma GMAT. So there will be two input objects. Finally, those different kernels can be collected into some packages, as we call them. And so in order to use a package, the user can just specify those kernels as a parameter to the graph when the graph is compiled. So when the graph is compiled, G-API will look into this kernel package and understand, so what I should use for this or that particular operation. Do I have enough kernels to run this graph? And after those kernels are identified, G-API automatically divides the graph into partitions called islands, where every individual island is executed by the specific backend. And here's the idea. So we can start with a very simple operation where we have operations A, B, and C in our graph. And this whole graph runs on image data, so it starts with GMAT and it ends with GMAT. And there is two intermediate GMATs. So A consumes GMAT A consumes gmod0 and produces gmod1. And this gmod1 is consumed by operation B. Operation B provides gmod2, and operation C consumes gmod2 and gmod0. So we have this long arrow from the beginning to this end of the graph. And finally, we have gmod3 as a result. So based on how we find kernels for operations R, B, and C, and how do we associate these kernels with operations R, B, and C, we may have different internal structure of our heterogeneous graph. For example, if all operations A, B, and C fall into the same backend, for example, be it OpenCV backend, then we can. So if we have operations A, B, and C all associated with a single backend, then all those operations will be kind of fused together in this single subgraph. And in fact, our graph execution will be defined by this backend execution, because A, B, and C have the same affinity. They are executed by the same backend. And this backend may or may not optimize out this internal execution. For example, if it is an OpenCV backend, then A, B, and C are just OpenCV functions. And as we know, the classic OpenCV functions cannot be optimized together, right? So it means that A, B, and C will be triggered in a sequence by OpenCV backend. However, if it is a fluid backend, or maybe it is an OpenCL backend, or maybe a PlayML backend, we have one for a tensor compiler by Intel, then A, B, and C become a single fused computation. And in terms of fluid backend, the B buffer will be optimized out. It will be completely transferred to user. User have no access to this object B because it is some internal portion of the graph, and its memory will be allocated only to hold this a certain number of lines to make operations A, B, and C execute. If, for example, A and B operations fall into one backend and C falls to another, then we can have configuration like this. So A and B will be executed by a single backend, and C will be executed by another, like by OpenCL, for example. And in this case, gmod1 can be still optimized out if it is a fluid backend, for example. But gmod2 will be managed by G-API itself, so it won't be part of any backend. It will be passed entirely to this next island in the graph, to the next subgraph, where this operation C will be triggered. And the same about this case when we have B as a different backend, so we cannot fuse anything here. A will be executed in one backend, and C will be executed in another backend. So we cannot fuse A and C here because we will get a loop. Our model is directed at cyclic graph. So with a loop, we just cannot execute this graph properly. So long story short, this slide demonstrates how internally we can decompose or distribute the graph on multiple devices if we are running our graph with multiple backends. And those different backends are providing different capabilities. For example, we can have one running inference on GPU and another running, for example, a stereo operation on CPU, or some bilateral filter on GPU. And in this case, all those three parts will be associated with different backends within G-API, and they can, in theory, continue executing in parallel. So the idea is that user don't need to care about this, and it all happens automatically. So if such capability exists, G-API leverages it automatically, and no any extra experience or effort is required from the developer in this case. So I think we can start with some more advanced topics like inference and streaming. Inference has been introduced in G-API model in 2019 in OpenCV version 4.2. So starting with that version, we now can handle infer requests within our graph. So as any other operation, infer request looks like an operation in the graph. However, it is different because it is always the same operations infer. So comparing it to some earlier operations like blur or subble or resize, those are different. And infer is kind of uniform operation. How do we run different networks using infer? Infer is a template operation. So we pass this network identifier, as we defined earlier here, as a template argument. So for example, if we have object detection and object classification, then we have two different network defined as operations here with a special macro G-API net. And then we can use them as part of the inference. So the idea is that inference and the way how this inference executed are again decoupled. So this pipeline can stay neutral from a particular OpenVINO backend or maybe ONX backend. And when we compile this platform on some specific platform or run it with some specific hardware, then we can switch how do we run inference in our graph, but not change the way how our graph is written and not change the way how the algorithm is written when this graph is using inference. So G-API infer T, as I mentioned, is a generic operation where T is a network we want to run. So far, we have two inference backends which implement this infer operation. It's just OpenVINO inference engine by Intel and Microsoft ONX runtime. So with the inference engine and OpenVINO, we can pass IRs to the graph when we want to associate this or that network with a particular model which we want to use for that purpose. And with ONX runtime, we can use ONX models natively with no need in IRs or any other inference engine specific structures. However, the most performant path is inference engine in our case because we do a lot of extra optimizations on how much infer requests we can trigger the interface of customizing and parameterizing inference engine is more rich just because it is available to us. So this is an example of how this object detection can be configured to run through inference engine. So we again separate operations from kernels, and as we do for interfaces and implementations. And while we have this object detection network defined, we can use it with different backends. So for OpenVINO, we have to specify this special structure CV G-API params specified to object detection object, so that the proper backend will be used to run that particular inference. If we will use CV G-API ONX params specified with this object detection network, then the body of the structure will be sort of different. We'll pass different parameters here. So this is a way to link different networks with different inference backends, which can run models. So in theory, we can combine OpenVINO and ONX runtime in a single graph. However, normally we use only one of them. So for IE, we have to specify XML path, a path to this IR file of the model. We have to specify path to the weights, where the trained weights for this topology, and a device string. That's a minimum. So device string may be CPU, GPU, as far as MyriadX and other devices supported by OpenVINO. After such object is created, we can wrap it into a network package, like we do with kernels, and pass it to the pipeline when we compile it as a compile argument. So when the graph is compiled and G-API is starting to associate the graph structure as it is defined with objects inside the available capabilities, it looks for networks of this type object detect. And once it finds it, it decides, okay, this is the parameters I have. I'm compiled with that parameters. I will use OpenVINO for that. And this is a backend I will use to run this network when the graph is executed. So another example of how to use this is Edge Gender network. from OpenVINO models. So this network calculates age and gender. In this case, we have two outputs, and this network should be defined with two outputs. And in order to specify which output stands for what, we have to call this extra method configure output layers on this parameter structure to bind it with certain output layers of the network so that it will be used properly in the graph. And we pass age and gender information properly to this operations, which will, for example, turn it into annotations or filter out objects by age within the graph. The next item is Streaming API. So Streaming API is, well, it is not kind of API, it is an execution mode. And this execution mode has been introduced in assumption that when we build a complete pipeline with G-API, starting with some I/O or image capture, including different blocks like decode, pre-processing, inference, visualization, we assume that on our heterogeneous systems, those blocks can run in parallel because they can be executed by different devices on a single SoC. So if they can be executed on a single SoC, then the execution model like this, a serial execution model, is not very optimal because we have this capture followed by decode, followed by resize, followed by inference, followed by visualization, all running sequentially. However, if these blocks can run parallel, we can shorten our latency like this. So just compare these two pictures. This is the frame execution time. We have this execution sequence for the entire frame. For example, for frame n-1, we end up with visualization, and then for frame n, we start with capture, decode, and resize, and again for the whole sequence. And then for frame n+1, we again start with capture after this visualization is done. So obviously, this execution model is not very optimal if we can run these blocks in parallel, and we can make a pipeline like this. So at the very moment of time, we can have data from different frames running in parallel on different devices. So it means that our frame for camera C6 is being captured in parallel with decode and pre-processing happening for frame 5. And at the same time, inference, for example, on FPGA can run for frame 4. And visualization on CPU can run for frame 3. And frame 3 will be our current result at time point T6. However, we don't need the entire frame to complete to get some new result for frame V4, because that's a pipeline, right? And in the time period T7, we get this result of inference visualized by block V4 immediately, right? Because we started its execution somewhere quite in advance. So the idea is that if we follow this path in this graph, we will find that the latency of the pipeline didn't change. So we still have to first run this capture, then run this pre-processing with decode, then run this FPGA inference, and then this visualization. So time from start to end, the latency for a frame doesn't change. However, we get results more often, and we get some more dense output stream, and the throughput changes dramatically if we implement an execution model like this. So the idea is that, well, I hope this method is quite old and it is quite classic, and it is quite hard to implement if you have an algorithm, which you can change them sometimes. So once you implemented it manually, that's it. If you want to modify it or you want to change your algorithm, you have to rethink the way how you implemented this pipeline model. And you have to rethink the synchronization, trading between different blocks, etc. So we decided that with G-API, we can solve this problem technologically. And once the graph is defined, again, once, we can easily implement this execution model for free. So when the graph is altered, you don't need to reinvent all this pipelining. It will be automatically changed to this updated graph if you added one more operation or removed one operation or changes the way how things are connected. So this execution machinery will be automatically generated by G-API to run for this new graph. So The idea is quite easy. So previously we had this G-computation object, which we could run on a video stream by running this method apply, which I already used in the samples. So we get every new image frame from the video capture. We run the cycle on our own, and we pass every input frame and every output object to store the outputs to the G-API in a loop. So we optimize this loop ourselves. In this case, this pipelining cannot be possible because we will run the sequence of operations with no overlap between each other. So it will be like the whole pipeline followed by the whole pipeline followed by the whole pipeline. In the streaming mode, which was executed in version 4.2, we introduced the streaming mode where the same graph defined by the same G-computation can be compiled for streaming with a separate method, and then specified with an input source where to take data from. So we have a ready-made wrapper for G-capture, for video capture, which is called G-capture source. So this code is kind of equal. However, in this case, we have this complex pipelining model implemented automatically once we start the pipeline. And all we need to do at the application level is to just start it, and in an infinite loop, start pulling the results from the pipeline. And all this aggressive parallelism with multiple blocks involved, it all happens inside. We don't need to do anything to do that. So that's the idea. Unfortunately, this presentation is already quite long, and I cannot show all the details about this, but this article actually defines and describes this concept pretty well, and also gives some performance numbers we measured in our lab for the privacy pipeline sample. Probably the last item among the features is Python API. So Python API has been introduced in version 4.5. And Python API basically allows to do everything what I showed already in this presentation. So we can build graphs, we can execute them, we can write our own operations with some specific Python interface, and we can run these DL models with OpenVINO in the backend only so far with Python API as well. So there are lots of samples available in the OpenCV repository. So under the G-API directory, it is either MISC Python samples or MISC Python test. In samples, there is a full gaze estimation sample available, which runs 4 networks in parallel with non-trivial pre- and post-processing around them. So for those who are curious, I really recommend to dig that sample. And it is actually a Python version of gaze estimation sample from OpenVINO Open Models, which is C++ based, and we do have our C++ based version there as well. So if OpenCV is compiled with Python support, G-API should be exposed there by default. So you can import CV2 as CV in Python and start using G-API with no problem. OpenCV is using its own way to connect CV data with Python data. So by default for images, it is NumPy is used, and NumPy buffers, NumPy arrays are used to represent image memory. So we follow the same concept, we follow the same conventions. So after you define the graph, this is very similar to a C++ code. And for example, you decided to use a fluid kernel package to run it in a cache-efficient manner. You can pass NumPy arrays directly to the apply method, like with OpenCV. So this conversion from NumPy to CVMet to associating with GMet will be done automatically. The custom operations can also be executed and written in Python. So maybe in Python they look more clear than C++, I have to admit. So for example, for bounding direct operation, we need to use a syntax like this with this at sign in the beginning, then specify what is the name of this operation, what kind of inputs it accepts, and what kind of outputs it produces. So bounding direct takes array of points and reduces a rectangle which encloses those points and covers it on the plane. So since it is an operation, we still have to produce this outMeta object method. But for array data types, we don't need to specify anything specific. So it's just an empty descriptor, like a placeholder for the future. And finally, the implementation of this bounding direct is again as OpenCV code. It may be a custom code or maybe a NumPy code, by method you can type here. So we have to define like kernel and define the class under a certain name. When we define the kernel, we refer to the type we are implementing. So this is an identifier of our operation we defined on the previous slide. And then we have to define this single method run, which takes the single input because this kernel has been defined with a single input, and produce a single result, which in this case, CV bounded direct of a P array taken from array. And it is, again, quite easy to use as well as in C++ code. We run this bounded direct on our input in order to produce outputs, and then we run this graph to get actual points. So it is pretty useless for a single node graph, but it makes a lot of sense when you're running on a complex algorithm and you have to combine G-API methods with inference, with custom pre and post processing code where everything should be connected. Again, gaze estimation sample, which I mentioned, is a very good example of it. So please check it out. So among the last features, we have in progress the integration with OneVPL, media framework by Intel for decode and for input, and the ongoing integration with GStreamer framework, which is already in OpenCV open pull requests. So that instead of video capture, as I used in my streaming examples, we can use a GStreamer pipeline, which can be complex, which can receive data from network or from some camera, from VP interface, used some native decoders like VA API, and we can share this memory from GStreamer into the pipeline with no extra copy. And same applies to the EPL. So the idea is to feed our graphs with data from external sources with no any extra copy or processing. And as part of this, we are also exploring this GPU memory sharing questions between media and inference for the inference backend right now. So I hope that in version 4.5.6 or maybe even 5.0, this effort will be complete. And final section of this presentation is some measured numbers for cases where G-API actually makes sense. Some of this data is already in the article I mentioned earlier about streaming and pipelining. And this presentation mentions the classic computer vision effects, classic CV effects where G-API was originally designed for. So the soluble edge detector runs on fluid backend with factor of times less memory than OpenCV consumes. For example, in 4K, the naive algorithm in OpenCV would consume 500 megabytes, and with fluid backend, it is around 1 megabyte, just a little bit, or kilobytes on top of that. So the factor is really scaling. This is one of the strong points. So for classic image processing, we can save lots of memory using that row-by-row execution model I explained by covering the fluid backend. Here goes the performance as well, because the less memory we consume, the less cache misses we have, and when all this memory is located in some tiny fraction, it can fit into this cache perfectly. So for the same resolutions, the same algorithm gives observable increase in performance when compared with naive OpenCV version. So we don't need to process the entire image. We don't need to evict lots of image buffers from the cache in order to then get them back to cache to process by some next operation. Instead, G-API can hold the entire image in the cache and make the processing quite faster compared to the traditional methods. This graph summarizes it for different resolutions. The larger image we have, and UHD is now pretty common, like FHD, we have quite significant performance gain over this traditional model where every function is executed individually. I believe that's all for now, and there is a number of items. I'm yet to update this slide with some recent information, more samples we have in models now, but you can always find this article, the code in OpenCV repository, where standard model from starting with 4.0 and a number of tutorials in OpenCV documentation, in the OpenVINO documentation, and this overall documentation chapters in OpenCV may be also quite useful. Thank you. Meanwhile, I can run a demo.
Yeah, sure. Yeah. Sure.
This is an edge detector which I presented, runs on some public video from the internet. The article is based on the same video, so we can see that the video is quite short. The result is quite interesting, but the real question is how much memory it consumes. Right? This is demo.exe. I will try to capture it using the task monitor. It's maybe not the best way, but I will try. So for this version, it takes about 100 megabytes, right? Demo, yeah, 108 megabytes. And it is the standard version which runs through OpenCV backend. Now let's make it run through Fluid backend. So this is a code. It is a code from the article with some extra input and output handling around. So let me do it this way. I will define a kernel package, which is CV G-API combine. Combine stands for combining different packages together of CV G-API core fluid kernels and CV G-API improc fluid kernels. So this method's kernels, they return a kernel package, a collection of functions you can use instead of the standard ones. Fluid is the backend, so we expose backends with these kernel packages. So in order to make it active, we need to specify to G-API. So we only calculated this package here. So now I'll pass it down as a compiler of this package. I hope it will compile. Yep. So the new version is compiled. Let's run it now and see how much memory it takes now. Where is it? The same video. So now we can see it runs with 46, 44 megabytes. The video is a little slow because the Fluid backend runs in a single thread as opposed to OpenCV, which runs in multiple threads. However, we're in progress with getting more trading support to that backend. However, the result is quite interesting. We only changed a few lines in our code, and we managed to save up to 50% of memory. And I would say that the remaining 40, it is video capture, which is already quite heavy by itself, which we cannot optimize out. So if you're using video capture, you always pay that cost. So it is kind of constant that. So in fact, we saved almost 50 megabytes of memory to kilobytes, right? So it is 2x, but on larger pipelines, it will be quite bigger number. Okay, maybe I can also show example here. So this is a privacy masking camera example from the tutorial. Yeah, on the same video. It runs on GPU, so it will load a little bit slower. But the interesting part here is that it runs two models, one to detect faces and one to detect license plates. Then we apply some transformation to hide this sensitive information from there. And the idea is that we can run those networks on different devices. So here I'm using CPU for vehicle detection and GPU for license plate detection. And here we go, we have these faces wiped out. We have this license plate also hidden. So this sample has reported 40 FPS for me. So now if I change the script to run it both on CPU, so I will choose the FP40 for here. Let's try it one more time. Yeah, so it runs quite slower as far as I see, because both networks are running on CPU and it produces only 21 FPS. So the key thing here is that we can easily run this pipeline heterogeneously by just changing a couple of parameters. And this parallel execution of those two different devices, CPU and GPU, happens automatically at the G-API level. So developers don't need to care about that, how to make it run parallel. We kind of sort it out by the framework. So people can focus and keep focused on the algorithm itself, not on the way how to execute it properly. So I believe that's all, and I can jump to questions.